Okay, good morning, everybody. One question, somebody's asking about homework number 9, if you needed to check for deflection. When, when the problem asks for deflection, they will tell you use L over 360, L over 240. If I want you to compute the deflections, I need to tell you, like in here, I'm saying check for shear. I need to tell you check for deflection, and I need to give you the deflection limitation. I cannot tell you check for deflection. I need to tell you the limit is L over 360, L over 240. So in any homework, you have to do what the textbook is asking, and whatever I'm adding, like in here, I'm adding that you need to check for the shear. Since, let me see how many people we have right now. We had 34. Okay, I'm going to talk about the exam. Remember that this homework is due on Monday. Until midnight, you have time to turn this homework in. And also, be careful when you use the solution manual, because the solution manual has some mistakes, and also they skip some steps. So there's nothing wrong with using the solution manual, but use it as a guide. I told you, and I always tell you, read the problem, because this is very interesting. I asked for the lightest, and not too many of you found the correct section. You didn't give me the lightest. Also, if you look at what is this? What is this in here? What I'm giving to you? Anybody? What I'm giving to you? What did I give it to you in here? What is this? Yep. And some people decided to select a different size. They went to the maximum, the minimum, and they use a different size. And one critical answer that a lot of people got it wrong was the thickness of the plate. And also, some people, they said that the grade or the steel for the gusset plate was not given. So everything was given, but a lot of people didn't read the problem. So obviously, you need to use all the limited steps. And in here, I told you that was a tension member. So remember, there are two of them. So each one of them takes 50% of the load. So some people started with yielding, the tension yielding, that was the right way. And they found the area based on 308. They found the area based on 308, and they multiplied that area by 2. So they were designing for 316. So I don't know why they did that. The other mistake for tension rupture, you need to assume, if you wanted, you needed to assume a value of U. Many of most of you assume 0.9. Some people assume 0.8. But a lot of people assume 1. You cannot assume 1 because you're using less than 100% of the cross section to transfer the load. And whatever assumption you make, you're supposed to check it. Once you design the well, you're supposed to check your assumption. Many people didn't bother to check the assumption. And also, the thickness of the plate, you could have found it by using block shear, but the most important equation to find T was the well capacity, because when you check shear yielding and shear rupture for the channel, it was okay. But the critical was the shear yielding and the shear rupture for this plate. So the critical value to determine the thickness of the plate was the shear yielding and the shear rupture. Why? Why was the shear yielding and the shear rupture critical for this? Anybody? Somebody got this. Some people got this right, but why? Yes, that's the answer. You getting, you have weld on this side and weld on that side. I did indirectly this problem in class. The only difference was that we had a web or a wide flange, but a lot of people failed to do this. And also in class, I mentioned to you, I said when we had a face-to-face, I have forgotten to show you this. This is page 19, but I did show it to you in our virtual classroom, and also there is a video of this. I want you to look at this. To determine the thickness of the plate, one eighth instead of 1/16, 1/8 instead of 1/16, whenever you have from 3/8 to 1. So many of you at only 1/16, you're supposed to use 1/8. I didn't take point off, but don't forget about that. And remember, we were using longitudinal and transversal weld. So we were supposed to check the two equations. One equation that the capacity of the weld for longitudinal and transversal are the same. And the other one was when this is 0.85, longitudinal 0.85, this is 1.5. And also, some of you, and you have to be very careful, you found the weld or the total weld for 308, and you put it on only one channel when you had two channels. 50% of the weld goes here and 50% goes in there. So those are the most common type of mistakes that I found in this problem. This problem was a Christmas present in April. And I did this in class, but a lot of you were not paying attention. Some people did it for grade 55. Some people did it for grade 50. Some people did interpolation. I'm going to tell you why you cannot do an interpolation. And in chapter E, you are familiar with this chapter. And in this chapter, a lot of you know that this is the equation for inelastic buckling, and it's called now flexure buckling. And of course, this is the equation for elastic buckling. But look at this equation. Is this a linear equation? Is this equation of a line? Anybody? No. So you cannot do a linear interpolation. You have to use this equation, just for some of you. Going back to this problem. The most common mistake. Well, some people didn't realize that this is the weak axis. We only brace the weak axis because that is without brace, it's gonna buckle about the weak axis. So we brace the weak axis. So that was 14, 14, 14. But the biggest mistake, look, we go with the largest KLY, the largest KLY. And so the majority of you said 14, 14.8 times 14. 0.8 times 14 is smaller than KL equal to 14. So 0.8, this one did not control. This one did not control. This was the one that controlled. But most of you made this mistake. KLY was 14. It was not 0.8 times 14. Also, some people didn't know where to find the K. So many times we've done it in class, got the wrong K. But it was a very easy problem. The other mistake was some people forgot to check for local buckling. The B over 2 times the thickness of the flange is this value. Some people made a mistake and consider this again divided by 2. So B is all of this. B over 2 times the thickness of the flange and H over TW. Now, most of you check for local buckling, some of you got the wrong equation. But some people that were following the example that I did in class, had a problem, had a slender flange. So we had, besides flexural buckling, we had torsional buckling. In this problem, we did not have torsional buckling. So if you did torsional buckling, was because, I don't know, that you were just following the wrong example, but there were no local buckling. So there was no torsional buckling for this problem. But this problem is a very easy problem, but a lot of people got it wrong. But I gave you some points with it. So the type of ball was a 3/4 inch A325N, and the entire connection was made out of A36. The entire connection made out of A36. So some people said that the grade of steel for this plate was not given. They said that I don't know that this type of steel. Other people say, I don't know the thickness of the plate. Look, some people say, I don't know the thickness of the plate. But in here, there were 2 problems in one. This is a tension member. This is a tension member. We use this gusset plate to transfer the load to this member here on the top. And this was a single angle. I did not want you to compute anything in here, but what happened to these 3 bolts. So there were 2 problems. This is a tension member. I applied the load at the centroid. So some of you didn't check that and found eccentric shear. There's no eccentric shear in here because it's applied at the centroid. This is a typical tension member. So to find the tension yielding was very easy because you went to the code and found the gross area. To find the tension rupture, look, the cross section had 1 hole, only 1 hole. Some people consider 5 holes. So this is the typical problem for exam number 1. The gross area is the net area times the factor U. And the net area, gross area minus one, only one hole in here. And to do the net area, remember there are two angles. Some people only use one angle. So, like any typical tension member, the net area was equal to the gross area minus one hole. To do, because we're using less than 100% of the cross section to find the value of U, 1 minus X bar over L. And L is from the first to the last bolt. So look, 1, 2, 3, 4. 1 minus X bar over L. What was the value of X? Anybody write the value of X for that equation? U, 1 minus X bar over L. What was the value of L in there for that equation? Good. You got it wrong. Somebody, a lot of people. This is a problem with double shear. Double shear, double shear, double shear. And in here, what we had on this triple, double or single shear? What do we get? Single shear. So when people found the capacity of the connection based on the bolts, and we're talking about this connection is different than this one. To find the capacity of the connection based on this bolt, you need to multiply times 1, 2, 3, 4, 5 volts, because these aren't a different member. Some people multiply 1, 2, 3, 4, 5, 6, 7, 8 volts. We only have 5 volts in here. And to do the block shear is the typical L. Some people got it wrong, especially the computation of the area. There were two angles in here. But bearing was a nightmare. People got bearing wrong. Because to do the bearing, we had the plate. Everything is 836. So the plate had half an inch that was given. And the angle had 2 times 5/16. Which one is critical, the plate or the angle? Anybody? Plate. And people check the angle, got it wrong. But all of this was not as critical as the top. Look, the question determines the maximum factor load safely applied to the connection. So this load here, and somebody asked me during the exam about this. This load in here goes all the way to this. It becomes eccentric shear for these 3 bolts. Now we had eccentric shear. So this TU that is unknown, this force, unknown force, is going to go all the way to the top. TU, PU is in here. Now we had eccentric, a very simple eccentric connection. This TU divided by 3, 1, 2, 3, shear, direct shear, 1, 2, 3, direct shear in the Y direction. We do not have direct shear in the X direction. And the moment TU times 3, 4 times distance in this direction. So we're going to have component in the Y due to the moment. So it was the moment was equal to 3 TU, the value of X was 3, and summation of X squared plus Y squared was 3 squared plus 3 squared. Only one person got close to this. So everybody else, the connection failed. But because of the situation that we are online, you are overstressed, I gave you some point. I was very generous grading this, but you have to understand. And I told you in class, you have to see what the force is doing. The more we go into this course, the more careful you have to understand what is the force doing to my member. This was a typical tension design. This was a eccentric shear design. And so once you find the resultant force in the critical ball, you have to make equal to the capacity of the ball. And the capacity of the ball was this ball in single shear and not double shear. And the force that you find, that's the answer. You don't need to multiply 1, 2, 3 because you're going to fail it. Remember, whenever we find the resultant force, we make it equal to the capacity of the ball. So this force is what is going to control your design. And so please be very careful, understand the problem. Don't follow examples just by looking at them. Understand the question. Understand the question. And the problem that we had really is understanding the behavior. What is the force doing to my connection? Hopefully you get it right for the final exam. Any question? A higher grade. The higher grade was 120 and the lowest grade was 40. Definitely, it is possible to see your exam. At the next exam, finally, when I was grading the other exam, the structure exam, I learned how to do the grading online. So next time, I'm gonna do all the grading online, so you're gonna be getting everything immediately. But don't forget that whenever you scan, make sure that you do a good scanning and you send a picture. There's nothing that I can write on the exam. If you send me a regular scan, the same way that I do it by hand, I will do it by using Blackboard. And okay, well, we need to continue with this course. We had 3 weeks left. I uploaded yesterday very old exams. And I want you to be careful with the exams that deal with beam columns because chapter 6 in the code had changed. It's a completely new chapter. But if you look at the solution from the old exam and you follow the new code, the answer is going to be exactly the same. And so if you look at a whole bunch of computation, especially for beam column, don't worry about where I got the numbers. Just use the new code. The solution is going to be exactly the same. The average, Ali, I haven't been able to compute the average. I've been grading like crazy. I'm now grading still. But the only thing that I know right now is the higher grade 120, the lowest 40. I've been trying to solve this problem for 2 weeks now. And you do need to read the problems carefully. In the exam, I couldn't believe I gave you the size of the well. People are still selecting a different size. I gave you the thickness of the plate, and people say, I don't have the thickness of the plate. And something that I forgot, I was asking for a channel, and some people gave me a wide flange. So there are different degrees of understanding, and so please read the problem carefully. And in this chapter, we had full support of the compression flange. Today, if I had time, I'm going to do a different type of problem. But this means from now on, no lateral torsional buckling. Whenever we had continuous support, there's no lateral torsional buckling. We can go and use the table in chapter 3, table ZX. However, we could have local buckling. And so this problem, I had designed to have local buckling, but there's no lateral torsional buckling. So another problem that we're going to have in here is that you have to compute the maximum shear force, you have to compute the maximum moment, and I want to see you work. For instance, in here, the moment that we had to design for due to the point load 1125 pu due to the weight of the beam, and this is a heavy beam, 4354 kip per foot. So on the next page, most of you had no problem with the moment inertia. We didn't have to compute IY in here, but we had to compute the plastic module. And the plastic module, what we do, we consider the entire area because the integration is over the entire area. But because of symmetry, I had considered the top and multiply times 2. So it's going to be this area, the first moment of this area, that is 16 times 0.5, times the distance from this centroid to the neutral axis or to the centroid of the entire cross-section. And it's not the distance squared. It's the first moment of the area. So this area times the distance from the centroid of this area to the centroid of the cross-section. This area times the distance from the centroid of this area to the neutral axis. This is what I had done in the next page. There are two areas. So the area on the top and the distance from its centroid to the centroid of the cross-sectional area. A little area times the distance from its centroid to the centroid of the cross-section. So this is 381 inches to the always the plastic modulus is larger than the elastic modulus. The relationship, like I mentioned the other day, between the plastic modulus and the elastic modulus is SF. The ratio between this and that is called the shape factor. Shape factor. And for a wide flange, between 1.1 and 1.2. And that means the reserved moment capacity. That is all that it meant. It had 10%, 12%, 20% more moment capacity whenever it becomes plastic. And this is to remind you that it is the integration over the area of YDA. And computed in here the local buckling. The local buckling, B over 2 times the thickness of the flange, give me 16. It's smaller than 0.38. This is lambda, this is lambda sub P. And this we know where to find. And H over TW, 26. And here I'm putting is case 15. So there is a problem. There is a problem here with the flange. So since there's a problem with the flange, because 16 is larger than lambda sub P, we have to compute the design capacity of this beam based on local buckling or slender flange. So here we had a problem with the flange. Before you ask me where we find the lambda, this table, you're already familiar with this table. You have used this table to do your homework. And remember, this in here, B over 2 times the thickness of the flange, that is indicated here. Look, also indicated in here for our case, because it is a built up. So this is the value of lambda, this is lambda sub P, and this is lambda sub R. Since we had a problem with the flange, because our lambda is larger than lambda sub P, we need to compute lambda sub R. and lambda sub r had a case of C, very similar to the exam. It had a new stress F sub L. This case you see is the same that you use for the exam. And the same limitation between 35 and 0.6. But this F, the new stress F to L, is 0.7 Fy. And here it said bending about the strong axis. And this is what you need to know. So get this patient you call, please. I need to tell you that. This value is equal to 0.7 Fy. And this ratio, the elastic modulus in tension and the elastic modulus in compression. So right now we are designing beams. So this is flexure, this is bending. So this is the cross section. And the way this is bending, we're gonna have tension at the bottom, compression at the top. So this cross section here is gonna have, this is the neutral axis. We're gonna have tension and we're gonna have compression. So this value in here, from the neutral axis all the way to the top, from the neutral axis all the way to the bottom. This is the value they call CT, and this is, sorry, CC, and this is C sub T. So this is the value from here to the compression to the farthest away is C sub C, this is C sub T. And if you remember from mechanical solid, sigma is equal to MC over I. So this is the typical flexure formula, and we rewrite it M I over C. So if you look at this formula, MC over I from mechanical solid, we rewrite it I over C. This is the value of X. Because bending is about the strong axis, we had SX. So that's why they had S to X compression and X to X tension in here. S to X tension, S to X compression. Right? Larger than 0.7, in our case, for this, our problem, what is the value of S to XT over X to XC for our problem. Anybody? 1, exactly. 1 because these two values the moment inertia I sub X is given here for the entire cross section. So in here we had I sub X divided by this value, I sub X divided by that value is exactly the same. When that would be different? In here, we only have one axis of symmetry. This is the axis of symmetry, the vertical. This is the only axis of symmetry. So in this case, we had C compression and C tension. In this case, in this value is this value equal to 1? In that case, in the case of the T. No. So you have to be careful. You have to be careful. That's all that I want you to know. So going back to our problem. Look, our flange is non-compact. I had computed already lambda of 16 larger than 8.02, and I compute lambda sub r. And lambda sub r is here the same case to C that you used before for the exam. For H of TW, it came larger than 0.76, we had to use 0.76. F to L equal to 0.7 Fy because it's equal to 1. You already told me that was equal to 1. So I put these values in here, and it came that lambda is larger than the lambda sub P, but it's more than lambda sub R. So we have to go to the code. Lambda larger than lambda sub P is more than lambda sub R. So we have to go to the code, to chapter F. We're going to this page, go to 16.1-49. 16.1-49. So we had a problem with the flange, and it could be also for the Y flange. This is a general example. So whenever we had a problem in the code on 16.149, so go to this page in chapter F, everything in chapter F. And I told you the other day that whenever we had a problem with the flange, we had to check both lateral torsional backlink and compression flange local backlink. Here we don't have lateral torsional backlink. So this is the formula that we had to use. The nominal capacity is the plastic moment minus the plastic moment minus 0.7 YSX. And in here we have lambda sub P of the flange, lambda sub R of the flange, and lambda sub P. So this is the equation that we have to use. M sub P, we're going to compute it because M sub P is the plastic modulo times Fy. S sub X is going to be I sub X over little c. So this is a section. The section is not a standard section. So it's not in the code. So we have to compute the plastic moment. This is yielding ZXFY. ZX we computed before. Fy is 65. Don't forget to divide by 12. In the exam for the column, some people forgot to multiply KL, forgot to multiply times 12. So remember, the unit, we had to divide by 12. So it came at 2,063.75 kPa. 0.7 FYSX, it came at 0.765. This is what I told you. We already compute I sub X, and this letter C Little c is the distance from here all the way to the top. So it is 13 plus 0.5. So in here, we had 1,241 K per foot. Always, because you are subtracting from the plastic moment, it has to be smaller than the plastic moment. If it becomes larger, you have a computational error. You subtracting from the plastic moment certain amount. So it has to be smaller than this value. And in fact, it is. So here's the computation. We have the plastic moment, 0.7, and lambda sub P, lambda sub R, lambda sub P. It gave me 15, 29, 27, smaller than this value, and times phi 13, 76, 34. And so, look, this number equal to the moment. From here, P came at 118.47. And this is PU. Came at 118.47, equal to 25% is the dead load, 75% the live load. It came at 75.92, the service load that we can. But we also need to check deflection. In this problem, the maximum deflection was given L over 360. We cannot exceed L over 360. 45, that is the total span, times 12 over 360, 1.5 inch. We cannot exceed 1.5 inch. The deflection limitation has to be given in the problem. Homework problem, exam problem, this limitation has to be given. So you had a computation, you know which number you cannot exceed. I mentioned the other day, I want to mention again, Deflection is a performance condition. Deflection is based on service load and only on live load. So the deflection, we do not factor the load. So I told you the other day, I'm gonna repeat it. When you get off your computer, repeat to yourself 10 times that deflection is a service condition. To compute the deflection, we only use the live load and we do not factor the live load. So we use what is called unfactor load. So we do not factor the load. So this deflection, the formula, everything is given at the end of chapter 3. And you have to be careful whenever you're using this formula because these are very simple shear and moment diagram computation. But sometimes the load moves to a different location. We had a combination of loads, so you do have to be careful. In many cases, we have to use virtual work to compute deflection. That is the fastest and the easiest, all of that. But this is given here, PLQ over 48 EI. So I came here and using my PLQ over 48. So in here, I don't know why I put this one, forget about this. But it's P, live, no factor. LQ had to be in inches. 48 is 29,000. I is what we computed, equal to 1.5. So PL from the deflection computation came at 5667. And the dead load condition or the problem is 1/3. So altogether, the service load is 75.56. So based on deflection, the service load is 75.56. Based on the moment, based on the moment, 75.92. And based on deflection, 75.56. Since this is a smaller disk control. Something that I want to point out again. In this problem, it is given that the live load is 3 times the dead load. That's why when I found the live load based on deflection, I divided by 3. I got my dead load. So live plus dead, 75.56. So in summary, whenever we had a problem, the next problem that I'm going to solve, all of them, they're going to have lateral support. So since this is a continuous support, we do not have lateral torsional buckling. Lateral torsional buckling is not a problem in here. And whenever we had a bending or flexural problem, we had to find the maximum moment, the location of the maximum moment, and we have to find the shear force. The shear force is going to be the reaction. And if this is given, we have to compute the deflection. So we're going to find values based on moment, values based on deflection, values based on shear. The smallest value control our design. Because if we use the largest value, we're going to fail the structure like you did in the example problem number 3. So we have to compute the moment. And after that, we need to see if we had a problem with the flange or the web. Any question about this problem? One going to be L for maximum deflection if we had 3 support. Okay. So what we have in here is an indeterminate structure. So indeterminate structure is a continuous method. In steel, if you've been to the field, you've seen passed by a construction site, still we are fortunate that everything is determinate. So we can solve everything with W squared over 8. We can solve everything as simple supported or a small indeterminate structure. In reinforced concrete, this is what we have, a continuous beam. Right? So if this is the case, right, in this course, we cannot solve this type of problem because for you to find the maximum moment, it takes you 1 hour, and it will take you 1 hour. You have 45 minutes to solve a problem like this, just to find the moment and the shear, right? But assuming that some information is given, you see, we're running out of time, but I want to answer this. Some people have to drive to the next class. So look, this is incredible what we had in chapter 3, because it gave you, look, continuous. They had 3 span loaded, the other one is not loaded. Look, all the shear diagram, this is what we do by moment distribution, all the moment, right? And look, computation of the deflection, this is incredible, right? So, and I tell you, sometimes you give me ideas for the exam, but when you ask me a question like this, it's a very good question, right? But I know certain limitations, and I want you to have enough time to solve the exam. But if you find a situation like the one the formula, so actually look, everything is given here, the deflection is given. Well, any other question because you have to go to another class? Look, everything, these are the L's, right? Between the span is the L. The deflection is between spans, like I had it in here. Between this is the L, this is the L, this is the L. I don't know if it was recorded. I have not gotten the last lecture. So if anybody has it, just give it to me. And also tomorrow we're gonna spend the whole time solving a different type of beams. And remember, In 3 weeks, we're gonna have our final exam, so everything gonna be beams and beamcom. Okay, any other question because you have to go. All right. Well, we'll see you tomorrow morning, 8:30. All right. Bye bye.